together, or say here there is no signal, so we know that signal and that signal are not coupled. So whatever nucleus or nuclear environment is creating those signals isn't coupled to each other. And so there's a number of different experiments where they do it in this way. And so one is COSY, which is homonuclear, meaning you just do hydrogen, hydrogen, and then you can determine the chemical, or you can determine which hydrogens are close to each other. But if you want, you can do heteronuclear, which is like HETCOR, where you do carbon and hydrogen. And so then you end up determining which hydrogens are connected to which hydrogens, and NOC, which is different. All right. I think that's it.
Okay, good, thank you. Any questions you wanted to ask?
I missed how so you run NMR and you want to know what's in your sample, right?
Yes.
I thought, okay, so don't you need like some data from like beforehand?
No.
Be like, oh, this P corresponds to a methyl group, this
Oh.
group, this.
Yeah. You do have generally known tables. So, for example, in this, if it's between like 1.5 and it would actually be 0 to 1.5 ppm. Generally, is the methyl group or methyl groups which are connected to nothing else, or the hydrogen is connected just to a carbon in the methyl group. And then the more electronegative the environment gets, you get further and further. They call downfield. And so then you have charts which say if it's in this range, then it's probably connected to something else. So for example, things way up here above, I think 7 ppm are connected to nitrogen, hydrogens, etc. And then in this range, a bunch of different sp2 hybridized things and ethers and esters really connected to an oxygen that isn't an alcohol. But yeah, but then I think the more important part actually is the splitting when you actually read the NMR. The more important part is the splitting because that tells you what things are adjacent. So you know it's not only important to know what it's connected to, but also how do things split. So if you have a sample and you have nuclei in a local environment that are going to resonate at a certain frequency, if their environment is similar, then they're going to resonate at a similar frequency. So if you were to look at one, you could have either the adjacent one up, contributing to the magnetic field, or down, opposing the magnetic field. So the environment that this one sees is dependent on the environment, or on how this one resonates. So then they'd have to be close in frequency in order to get that coupling.
More questions? If not, let's thank Brennan
No?
once again.
Oh, thank you.
So, by now, the information that we are getting is not yet sufficient for immediately diving into this research area, but at least it does show us a pathway that we are getting new dimensions and new skills to characterize behavior of quantum systems from different angles. So if we do have an opportunity to follow the phase of superpositional state, to create and to read them by short pulses and see how they evolve in time, so all the skills open us a door into a new popular application of modern days, so-called quantum computers. So it is so popular that there are 2 volunteers who, well, there were more than 2, who wanted to present this. So Samuel Brown will start, and then there will be another talk on this subject. Floor is yours.
Thank you. Yep, so I'll be talking about quantum computers. Just kind of an origin. So we all have heard of Moore's Law, where the number of processors on a chip increases exponentially with time. So that's Moore's Law. Here's just kind of an example of that. But at some point, this is going to reach a limit due to size restrictions and quantum effects, just as you gain smaller and smaller within the chip. Richard Feynman in 1982 proposed putting quantum mechanical effects hardware into these computers to make quantum computers. And then David Deutsch came up with a theoretical paper proving the probability or giving how this could actually work. So like with a quantum challenging or a problem with a quantum computer can solve is something that has like a number of processors or the the degrees of freedom increases exponentially with n. So the challenge as the size increases exponentially increases. So that's where we want to start to use quantum computers, because our classical computers don't work with these very well because they don't increase nearly as quickly. So a qubit, we all know that these can be a superposition. So here's just a block diagram where that qubit can be either the 1 or the 0 state or any superposition in that. And this allows us to have the superposition to have many different states. So let's just move on. So we have the wave function for this, where C0 and Z1 can be represented here, and this is supposed to be theta. That's our single qubit. So when we have these qubits, we want to be able to manipulate them like in a regular computer. So a regular computer has logic gates, so you have a input 1 or 0, and when it goes through the logic gate, it becomes either 0 or 1 depending on what it was and what that gate is. So like in a NOT gate here, you have these truth tables. So this A comes in, if it's a 0, then it just switches to the 1. So that's our typical classical computer, and there's several of these which I don't know many more of them. They're not the easiest, just switches signs. So we're going to try to look at these from like a computation or a quantum gates. So in the same way, we want to have an input qubit with a wave function here with the different coefficients, and that goes through our single qubit gate, and that comes out with a different wave function. So here I showed the NOT gate. On the other hand, here are some typical logic gates for a quantum system. So we have a NOT gate or an X gate, a Z gate, and then a Hadamard gate, H gate. So here's the matrix form of these different gates and how they'll operate on the matrix form of that operator, or on the wave function. So here's our wave function again, and if we're in this state, in the 0 state, this is our wave function in matrix form. And then if we operate on this with the NOT gate, we get it to switch going up. And so we can do this with the Z gate, the same thing. So in this case, we're in the 1 state, and doing this with the Z gate, we get another switch. And then the Hadamard gate, you can apply these to get different states within our system and can kind of control the states. Then there's the combined gate, the CNOT gate, which I don't exactly know how, but apparently with this gate and the like 3 other gates, those are like the primary things that you need to start making different things within your, like these are the basis of what you need to build up for a quantum computer. So here's the CNOT operator function, and then the what it does is it has a control and a target. So it looks at the control, and the control never changes. So here's the control will always stay the same in these inputs. So the control and the target. So the control doesn't change throughout these, but it looks at the control and then changes the target gate. So if the control is a 1, then it'll flip the target gate. So we'll just kind of go over a quick example of changing a state that's in the 0th state, where we have the Hadamard operator, and then going into that CNOT gate. So if we first have a state within the 0th state, we apply the Hadamard one here, which is this function. We get these 2 states, or the wave function in this state with the 2 different coefficients. And then we multiply again the 0 state here to these 2, which gives us this state. And then we can apply our the CNOT gate, which I showed in the previous slide, which is here, to this state, which is right here. And then we can get a flip of this state. So this is our outcome. With this, there's applications. So here's just a few different applications to some quantum systems that can actually be used, like a quantum dot. People have used it. You can flip between the excited and ground state. Photons, I think, can change with the polarization between horizontal, vertical. So a couple examples of how these can be used practically. And then any questions?
Thanks, Sam. Any questions to this to the presenter on this hot topic?
What's a qubit made of?
Yeah, so that's like the challenge and such. This is a few examples of where you could try to make them, like maybe with a quantum dot or something like that. I think I saw there's like a nitrogen vacancy. That's how you can try to get, because you just want to be able to control that thing with the external.
I've seen things like vacancies.
And that nitrogen vacancy, I think they have like diamond and they put in nitrogen of like ion implantation or something, and then they can get it. So you're just trying to control the wave function of something separately. I think there's challenges in trying to get them to be close enough to where they have coherence, and like practical applications, which I'm not in the field to know enough about what the practical applications are and such. And like they want it to be like room temperature, like that's the goal, have it room temperature where you don't have to worry about it as much.
So that will be a two-level atom?
You want a two-level system, two-level atom, something like that.
Okay.
More questions? Let's go to slide number 3, where you show 4 plus 5. So why 0, 1, 0, 1 equals 5? Or let's make a verbal quiz. So let's give a problem to Sam and he will solve it just from the top of his head. So let's suppose that you have record 3 qubits and they all are in the state 1. So 1, 1, 1. How to convert it into decimal? Which number will it be?
Is this a binary or?
Convert 1, 1, 1 from binary code to decimal.
It's been such a long time.
Anyone wants to help you?
I think I know. 7.
Yes! Very good, very good. So can you explain to Sam how did you do it?
Yeah, so the left or the rightmost run is the 1 spot, and then the next one is 2s, and then you just double it from there every time. So then the next one is 4s. So like in our system, the first one's 1s, and then it's 10s, and then it's 100s. Binaries, the first one's 1s, and then it's 2s, and it's 4s, and it's 8s, etc. So I just did 1, 1, 1, which is 1, 1 plus 1, 2 plus 1, 4.
So 1 plus 2 plus 4 equals 7. Good. Let's go to the slide number 9 with control note. Multiple choice quiz orally. And I invite everyone in the class to help if just that we do it quicker. So the conversion operator that corresponds to going from 2 qubits in initial state to qubits in final state is represented at best by one of the 3 mathematical concepts. Choose one. Hamiltonian, evolution operator, Liouvillean. Which one?
I'll go C.
Any other options? How do we go forward from the past to the future? Not infinitesimal, the longer times. Hamiltonian, Liouvillean, or evolution operator? Yes, yes. So the evolution operator that would physically represent this gate should look this way in the matrix representation. So it's not Hamiltonian, it's not Liouvillean, it's evolution operator. Good. More questions to Sam? If no, let's thank him once again. And last but not least, very important presentation by Levi Lustrom, and he will increase our knowledge in the aspect that was inducing the interest of the audience. So Diane was asking, what is the qubit? Or we were recently discussing which mathematical construction corresponds to implementation of the quantum gate. So Levi will review from his angle basics of quantum computing, and then we'll give an exact, explicit example how to implement this 2-qubit gate and how it works in details. Floor is yours.
So the beginning will be very similar to Sam's. So classic bit, we can do ones or zeros, so it's not that, and we have to have the same number of bits as we do the numbers, but if we go to quantum bits, if we have a 1 bit, then we still get 1 or 0, some linear combination, which is not as important, but as we increase the number of qubits, the number that we can get goes much quicker because we can get 0, 0, 1, 0, and so forth. And then, so if we go to 3, then we get 8 combinations, which is very preferred, and they're all linear combinations. And then they're orthonormal. So this is another representation. So we can do like C1, C2, which these are just the coefficients, and we can see that they grow rather quickly. So as Sam did, we can project it onto the block sphere, and then what's important is this quantum gate, because we go with all of our states and then we want to change them. So Sam talked about both of these already. So there's the single gate and the multiple gate, the 2 gate. So I'm not going to explain that again. So getting kind of into application, if we look at the like the sphere, and we want to go from state 1 to state 0, we can use the pulse area theorem to go from top to bottom, and we could do like a pi pulse or a half pulse, which would get us on both sides. So this is kind of the example. So if we have a system that has both down and then both up, we can get 2 intermediate states where we have the first system is up, the second system's down, and then we can do another intermediate which is the opposite, and then the top which is up, which is important. We want to have a slight difference here and here, so when we do different pulses at different energies, then we will occupy a state or deoccupy it. So going from 0, 0 is obviously nothing, but we can look at this where we go from 1, 0 up to 1, 1, and we would do a pi pulse at the energy that they say is omega A, so then we go from 0 down. But if you look at this, we would just do a pulse at omega B, so then we go from 0 to 1. So if we look here, we would go from 0 at this energy, so it only affects the second stage. And we go from 0, and then we do a pulse, and then we go up. So we can use, if these energies are correct alignment, so we don't get overlap, then we can easily do the 4 different states, and then that will give us our logic gate. And we can say, if we want to go from 0, 0 up to 1, 1, we can do we have to do a full pi pulse at both A and B. So in conclusion, quantum gates are much better. They can be on the block sphere, and then we can set up a correct system where the energy levels are finite so that they don't overlap. So we can do pi pulses to get different levels. And one example that a paper had was like a quantum dot, and then they're embedded so that you can shine different quantum dots with lasers, and then you can have a detector, and then that can be your qubit. Any questions?
Well, thank you, Levi, for being extremely quick in this complicated subject, and the presentation is open for discussion. Jabba?
How do you read that quantum bit?
What?
How would you read that information from this?
Perfect question.
That, I'm not, I guess I would intuitively think about like spins. So if you had spins, then you could look at the magnetic field, because up spin
Then
and
it
down.
will be changed.
What?
Then if you apply the magnetic field, that can change the spin of the system, right?
If you use something like a flux. So not applying a field, but just detecting a field. That's maybe one way. The quantum dots may be a bit harder to do it. I didn't look into how to detect it that much.
But what is your instinct or intuition? If you have spectroscopic quantum system and it is either in one or another excited state, how would you read in which state it is?
You could maybe shine, no, but then if you shine a light, then you ruin the system.
But do not restrict yourself, just unleash the imagination.
I guess if we're in like 1-1 and we shine this amount of light, then we know that we're in this state because that's the only state that has that light.
So you mean spontaneous, oh not spontaneous, induced emission?
Sure. So,
Or maybe something similar to the echo, that photon echo that keeps track of the phase, and this depends on the phase and superposition.
because all of these have different energies, right? So if we say we do a pi pulse on like omega A, then if it's absorbed, then that will say it's in a specific state. But if it's not, then it's in a different state for the first and second, the first qubit. So then you can do a pi pulse at B, and that will tell you which state both of them are in. And then you can follow it up with a second pi pulse in both energies, because then you will revert back to the initial state. But that would be my guess, I guess.
So how many lasers do you need to implement this gate?
Probably 4.
Okay, good. So now another question to you as to growing quantum chemist.
Okay.
Why 1-1 state has energy that is different from omega A plus omega B? Just in real life, not related to quantum computers, but based on your quantum chemistry research and background.
I would say they might be interacting, and that energy of interaction will raise it.
Yeah, it could be either increasing or decreasing, but like Coulombic interaction or...
Yeah.
Okay. More questions to Levi?
How do you store things in memory in quantum?
That's good.
I always wonder that. I can probably just look it up around later.
Let me reformulate.
I
Are you aware of availability of long-term storage for quantum computing, or everything should be done really quick?
I would say, from what I have read and my take on it, this is more the processor, not the storage.
Yeah.
So, if you want to store it, you're not going to store it in the processor itself. You're going to store it in RAM or something else. So this is for the calculations, if that makes sense.
Yeah.
So the storage time is limited by the time of free induction decay. Everything, processing, reading, storing should be done before it happens. Really quick.
Which
Otherwise,
is a benefit for if you're doing processes, because you want it to be quick. You don't want to have to wait a long time. Maybe saving the data will have a bottleneck, and then it will get ruined. But I don't know of any way to store on the system.
So you use classical computers to store, and quantum computers to
Compute.
compute.
There may be technical issues, but I didn't read into technical. It's still in its infancy, I would say. So there's a lot of questions.
That actually was one of my questions now.
What?
So like a couple of years ago, when I was thought this stuff might be cool, and I was looking it up, they still were at the phase of only having done like a couple of bits for millions of dollars. I think it was still all just completely prototype. Has anything changed or?
I didn't look into the real implementation, like real world.
There's supposedly a company called like the D-Wave or something that's got their own one, and I don't. It just kind of popped up out of nowhere in Canada or something like that.
So like it's a fully assembled computer?
It's huge. It's like a supercomputer, and they use like a super cooled type of thing for the quantum system.
And I think it has to be at like almost 0 Kelvin.
Yeah, it's very cool. But I think it has. They claim it does.
So which physical principle do they use?
I'm not sure.
Sam was listing like 6 possible implementations. So which of them are possible? Which of them are closer to commercialization?
I don't think any of them are close to commercialization.
Spin, polarization, excited state. Didn't mention the ultra-cold atoms, which may fall into one of this excited state, but it is a little different principle. When magnetic fields trap ions in vacuum, so they do not touch anything, and then the lifetime of excited state is a little longer than for other implementations. Okay, well, many thanks to Levi for presenting and for the discussion. So, with this, I would like to thank all presenters who covered all these interesting subjects. So, let's meet a couple of times more this week. Wednesday, 6 p.m. in the lab, and Thursday at noon at this room. And the next week there will be another conference that some of us are traveling to. So there will be another silent period. Okay, thank you and see you tomorrow.